Ever wondered what happens to everything that gets sucked into a black hole? Does it disappear, or does it go somewhere else? Just like the Bermuda Triangle of space, black holes are enigmatic entities that have puzzled scientists for decades. They're like the universe's greatest magic trick, seemingly making matter vanish without a trace. But where does all that matter go? And more importantly, what happens to the information it contains? Information, in the quantum mechanical sense, is a fundamental building block of our reality. It's indestructible, or at least it should be, according to our current understanding of physics. But black holes, with their intense gravitational pull, appear to defy this principle, giving rise to what's known as the black hole information paradox. This paradox poses a significant challenge to our understanding of the universe and the laws that govern it. Why is this paradox such a big deal? Well, it's because resolving it could lead us to a deeper understanding of our reality. It could help us reconcile the seemingly incompatible theories of quantum mechanics and general relativity, two cornerstones of modern physics. It could reveal new insights about the nature of space, time, and matter. And who knows, it might even answer some existential questions about our place in the universe. But before we can unlock these secrets, we must first understand the nature of black holes and the principles of information. We must delve into the intricacies of quantum mechanics and the peculiarities of general relativity. We must explore the possible resolutions to the paradox and the theories that support them. And we must examine the experimental evidence, or lack thereof, that could validate these theories. So, are you ready to embark on this intellectual journey? Are you prepared to challenge your understanding of the universe and perhaps even alter your perception of reality? If so, brace yourself, because we're about to dive into the world of black holes and unravel this mystery. Imagine a cosmic object so dense that nothing, not even light, can escape its gravitational pull. This is the premise of a black hole, a region of space where gravity is so strong that nothing can escape once it crosses the event horizon, the boundary around a black hole beyond which escape is impossible. Black holes are the ultimate cosmic quicksand, pulling in everything that gets too close. They're like a giant cosmic vacuum cleaner, sucking up everything in their path. But what happens inside a black hole remains a mystery. The laws of physics as we know them break down, leading to a singularity, a point of infinite density. Yet black holes are not just cosmic vacuum cleaners. They're also cosmic powerhouses emitting what's known as Hawking radiation. Named after physicist Stephen Hawking, this radiation is a consequence of quantum mechanics, the theory that describes the behavior of particles on the tiniest scales. Hawking proposed that pairs of particles and antiparticles are constantly popping in and out of existence near the event horizon of a black hole. Normally, these pairs annihilate each other immediately. But if one falls into the black hole while the other escapes, it can result in the black hole losing mass over time, a process we refer to as black hole evaporation. This radiation is incredibly weak, making it almost impossible to detect from Earth. But it has profound implications for our understanding of black holes and the nature of the universe itself. Black holes are fascinating for many reasons. They challenge our understanding of the universe, push the boundaries of our knowledge, and force us to rethink our most fundamental theories. They're the ultimate cosmic mystery, a riddle wrapped in an enigma, shrouded in cosmic darkness. Now that we've grasped the basics of black holes, let's look at the nature of information. Black holes, with their incredible density and powerful gravitational pull, are not only fascinating objects in their own right, but also the key to one of the biggest puzzles in modern physics, the black hole information paradox. But that's a story for the next scene. In the quantum world, information is a bit like energy. It can neither be created nor destroyed. This foundational principle is rooted in the quantum mechanical understanding of information. Now you might be thinking, what does it mean for information to be quantum mechanical? In the realm of the very small, where quantum mechanics reigns supreme, information is not just an abstract concept. It's woven into the very fabric of reality. It's embedded in the state of every particle, every wave, every fluctuation in the quantum field. This information, this quantum data, is what defines the reality we observe. For instance, the information about a particle's position and momentum determines its behavior. Change the information, and you change the reality. But there's a twist. Quantum information is not just defining, it's also indestructible. It's like a cosmic conservation law. Just as energy is never lost, only transformed, so too is information. It can be transferred, encoded, scrambled, but it can never be outright destroyed. This principle, the indestructibility of information, is a cornerstone of quantum mechanics. It's why your coffee cools down to room temperature, why light bends around a gravitational field, why the universe is the way it is. It's a rule that nature seems to follow without exception. Yet, as we've seen, black holes are the rule breakers of the cosmos. They bend and warp space-time, they gobble up stars, they defy our everyday understanding of physics. So it's only natural to wonder, what happens when these cosmic renegades come face to face with quantum information? Do they respect the rule, the principle of the indestructibility of information? Or do they, in their insatiable hunger, consume it, obliterate it, erase it from existence? These are the questions that form the heart of the black hole information paradox, a puzzle that has been baffling physicists for over half a century. But what happens when this indestructible information meets a black hole? This is the mystery we'll dive into in the next segment. So buckle up, because we're about to venture into the heart of a black hole. Here's where things get tricky. When information meets a black hole, it seems to disappear forever. This conundrum is known as the black hole information paradox. Picture this. You've got a book full of information. If you burn that book, the information isn't really gone. It's transformed into other forms like heat, light, and even smoke particles. Theoretically, if you could measure all these things precisely, you could reconstruct the original information. This is a fundamental principle of quantum mechanics, the indestructibility of information. But what happens when a black hole enters the scene? Say you toss that book into a black hole. The book crosses the event horizon, the point of no return, and seemingly vanishes from our universe. But what happens to the information in the book? According to classical physics, it should be preserved somehow. But how? It can't escape the black hole. So it seems the black hole has done the impossible. It's destroyed information. This is a big deal. It's like a cosmic crime scene. The laws of physics as we know them have been broken, and we're left scratching our heads trying to figure out what happened. The stakes are high. If information can be lost in a black hole, then it undermines the very predictability and determinism that underpin physics. It implies that the future isn't just uncertain, it's unknowable. We can't predict it, even in principle. The information paradox also shakes our understanding of reality itself. If information defines reality, as quantum mechanics suggests, then what does it mean if information can be erased? Does part of reality disappear? Does a new reality get created? The questions are as profound as they are perplexing. This paradox leaves us with a big question. What happens to the information swallowed by black holes? The answer to this question may hold the key to understanding the true nature of reality, the limits of physics, and the enigma of black holes themselves. Scientists have proposed several intriguing solutions to this paradox. And so, we venture into the realm of possible resolutions to the black hole information paradox. One of the earliest propositions is that maybe, just maybe, information is lost forever. This notion essentially suggests that when anything crosses the event horizon of a black hole, it, along with its information, disappears from our universe forever. However, this idea counters quantum mechanics, which insist that information can never be destroyed. So, while it's a possibility, it's not one that sits well with the laws of physics as we know them. Now, let's move on to a more exotic proposition. What if the information is not lost, but hidden? This theory suggests that when matter falls into a black hole, its information might be squirreled away in a baby universe or a remnant. According to this idea, black holes could be gateways to these baby universes, where the information continues to exist. It's an enticing idea, isn't it? But, as you might have guessed, it's also highly speculative and lacks concrete evidence. Then we have the holographic principle. This is where things get a bit holographic. According to this principle, all the information about what's inside a volume of space can be encoded on its boundary. So for a black hole, the information about everything that's fallen in could be encoded on the event horizon. That's right, the two-dimensional surface of the black hole could contain all the three-dimensional information about what's inside. This is known as the two-dimensional and three-dimensional duality. This leads us to the concept of the universe as a hologram. It suggests that what we perceive as a three-dimensional reality might actually be encoded on a two-dimensional surface, much like a hologram. This idea extends beyond black holes and gets us to question the very nature of our reality. But, as with all theories, it's still under scrutiny and is far from being universally accepted. These various solutions, each more intriguing than the last, all aim to reconcile the laws of physics with the existence of black holes. However, none of them have been definitively proven. Each theory opens up a new set of questions, and the quest for answers continues to drive our exploration of the universe. In this journey, as we delve deeper into the enigma that is the black hole information paradox, we find ourselves facing even more paradoxes. One such paradox that these theories lead us to is the firewall paradox, which we'll explore in the next segment. But for now, let's appreciate the intricate and mind-boggling complexity of the universe and the black holes within it. These theories, while fascinating, bring us to another paradox, the firewall paradox. So, strap yourselves in, because the ride through the universe's biggest mysteries is far from over. Quantum entanglement, a strange but fundamental aspect of quantum mechanics, plays a key role in the information paradox. Let's dive into this quantum quirk that Einstein once referred to as spooky action at a distance. In the quantum world, two particles can become entangled, meaning their states are intimately linked no matter how far apart they might be. Imagine two entangled particles. One falls into a black hole while the other is left outside. According to quantum mechanics, the outside particle should still be able to reveal information about its fallen partner. However, black hole physics suggests that any information that falls in is irretrievable, creating our paradox. Now let's introduce the firewall paradox. This is a proposed solution to our conundrum, but it comes with its own set of problems. The idea is that a literal firewall, a wall of high-energy particles, exists just beyond the event horizon of a black hole. This firewall would sever the entanglement between the particles, preventing any information leak. But here's the catch. If there's a firewall, then an observer falling into a black hole would notice something unusual at the event horizon, contradicting Einstein's theory of general relativity, which posits that falling into a black hole should be uneventful, at least until you reach the singularity. So, we're left with a choice. Either quantum mechanics is wrong, and information is lost in black holes, or general relativity is wrong, and there's a fiery death awaiting anyone who dares to cross a black hole's event horizon. This paradox is still largely unresolved, and it's one of the biggest debates in theoretical physics today. It's a reminder that while we have made incredible strides in understanding the universe, there are still mysteries that continue to baffle us, and black holes remain one of the most enigmatic. Stephen Hawking, the pioneer of black hole physics, also had some thoughts on this paradox. In his later years, Hawking proposed a potential resolution to the information paradox. He suggested that black holes might not be as featureless as once thought. Instead, they could possess what he called soft hair, subtle imprints left by all the particles they've ever swallowed. This concept diverges from the traditional view of black holes as simple, featureless spheres. In this revised theory, black holes are intricate entities, their surfaces a complex tapestry of information. This soft hair isn't physical strands, but rather a metaphorical term referring to the quantum information encoded on a black hole's event horizon. Hawking's theory of soft hair suggests that information isn't lost within the black hole, but is stored at its boundary. When the black hole eventually evaporates through Hawking radiation, this information would then be released back into the universe. While these theories are intriguing, we still need experimental evidence to validate them. The quest to fully unravel the mysteries of black holes continues. Testing theories related to black holes is a challenge, but not an insurmountable one. The difficulty lies in the fact that black holes are not exactly accessible. We can't just hop in a spacecraft, zoom off to the nearest black hole and start conducting experiments. But that doesn't mean we're at a dead end. Scientists have come up with ingenious ways to investigate the mysteries of black holes. One approach is to look for the effects of black holes in the universe around us. For instance, we can study the intense radiation emitted by material as it spirals into a black hole. This can provide clues about the nature of black holes and the fate of the information they swallow. Another technique is to create black hole analogs in the laboratory. Yes, you heard that right. We can actually simulate certain aspects of black holes right here on Earth. One example is the Bose-Einstein condensate, a state of matter that occurs at ultra-low temperatures. When manipulated in certain ways, these condensates can mimic the behavior of black holes, offering a useful testing ground for theories. Acoustic black holes are another fascinating example. These are systems where sound behaves in a way that's mathematically similar to how light behaves near a black hole. By studying these systems, we can gain insights into the phenomena that occur near the event horizon of a black hole. Of course, these lab-based black hole analogs are not perfect replicas of the real thing. They can't capture all the complexities of a genuine black hole, but they do provide a valuable tool for investigating some of the strangest and most intriguing aspects of these cosmic enigmas. The quest to understand black holes and the information paradox is far from over. It's a journey of exploration and discovery, full of challenges and surprises. And as we delve deeper into this mystery, who knows what we might find? There are also other theories of quantum gravity that might help resolve the information paradox. But that's a story for another scene. Loop quantum gravity is one of the theories that might provide some insights into the information paradox. This theory suggests that the fabric of space-time is not continuous, but rather consists of tiny, discrete loops. These loops could potentially store information, offering a way out of the paradox. There's also string theory, a popular alternative that posits all particles as tiny vibrating strings. In this view, information might be encoded in the vibrations of these strings, again suggesting a possible resolution to the information paradox. Finally, we have theories like quantum foam or causal dynamical triangulation, which propose a quantum mechanical understanding of gravity. These theories might offer novel ways to reconcile the loss of information in black holes with the laws of quantum mechanics. Each of these theories presents a unique and compelling perspective, yet none have been definitively proven. The information paradox, while complex, has profound philosophical implications. The information paradox challenges our understanding of reality and the nature of the universe. With this paradox, we're not just grappling with obscure scientific problems, we're stumbling into deep philosophical territory. Take, for instance, the idea that our universe may be a simulation, a holographic projection of information encoded on a two-dimensional surface. Sounds like science fiction, doesn't it? Yet it's a serious proposition put forth by some of the brightest minds in theoretical physics. It's a radical rethinking of what we mean by reality. If the universe is a hologram, then what we perceive as three-dimensional reality is just an illusion. We're like characters in a very sophisticated video game, unaware that our world is just a series of ones and zeros in some cosmic computer. Another philosophical implication is the question of human understanding itself. The information paradox is a stark reminder of the limits of our knowledge. It's a humbling thought that there may be aspects of the universe that are fundamentally unknowable, forever beyond our intellectual grasp. As we delve deeper into the mysteries of black holes, we're forced to confront our own cognitive limitations. We're reminded that our understanding of the universe is always provisional, always subject to revision in the light of new evidence or new ideas. This is not a cause for despair, but a call to humility and open-mindedness. It's a challenge to our imaginations, a spur to innovation. The information paradox pushes us towards the boundaries, towards the need for a new kind of physics, a quantum theory of gravity that can reconcile the seemingly irreconcilable. The micro-world of quantum mechanics, and the macro world of general relativity. In wrestling with the enigma of black holes, we're not just learning about the universe, we're learning about ourselves. We're exploring the limits of human comprehension, the boundaries of the knowable. We're asking profound questions about the nature of reality, the fabric of space-time, and our place in the cosmos. The quest to resolve the information paradox continues, promising exciting insights into the nature of the universe. The black hole information paradox, while perplexing, is a cornerstone in our quest to understand the universe. We've delved into the depths of black holes, explored the indestructibility of information, and grappled with the paradox itself. We've considered various solutions, from lost information to the holographic principle, and even ventured into the realm of quantum entanglement and the firewall paradox. We've also revisited Hawking's revised theory, contemplated the concept of black hole hair, and pondered on potential experimental evidence and black hole analogues. Alternative theories of quantum gravity and the philosophical implications of our findings have likewise been discussed. These discussions underscore the importance of black holes in our quest to understand the fundamental nature of the universe. As we continue to probe these cosmic enigmas, we inch closer to unraveling the mysteries of reality itself. Join us on this exciting journey to unravel the mysteries of the universe. Don't forget to like, comment, and subscribe for more intriguing content.